Hello, welcome to another physics lesson. Today we are going to combine the electromagnetic theory and some of the things that we have been watching in classical mechanics. Um, Today we are going to be working with a particle that is under the influence of an electromagnetic field. Okay, so here we will have two influences due to the electric field and the magnetic field. So we are going to start by proposing a Lagrangian that is going to depend on the magnetic influence and the electric influence. So let's say that we are going to define the Lagrangian L as 1/2 mb squared minus q, that is going to multiply a scalar potential phi of x, y, z, t, and then plus q times b dot a. And here a is, the function known as the vector potential. You know that, we can establish that the electric field is generated by some scalar potential phi with this relation, minus the gradient of phi, and then minus the partial derivative with respect to time of the vector potential A. Okay, and we also know that the magnetic induction, what we know as the magnetic field, is equal to the curl of the vector potential A. Okay, so we are going to establish that we have a Lagrangian for this particle given by this expression over here, and we know that this A and this phi, they are related with the electric field and the magnetic field by these two equations. So what we are interested in is to see what happens if we take this Lagrangian into the Euler-Lagrange equations. So first of all, let me rewrite this Lagrangian as 1/2 m times x dot squared plus y dot squared plus z dot squared minus q phi plus q, and then the dot product between b and a, but that is going to be x dot ax plus y dot ay plus z dot az, where of course we know that b can be seen as x dot y dot z dot. Okay, perfect. So also recall that the Euler-Lagrange equation that we are going to use, we will have three equations, right? One for each generalized coordinate, but we are going to work out just with one coordinate, and then when we get the result, we are going to generalize to the three coordinates. So all the process we are going to do is going to be with the x coordinate, okay? So we will have that the Euler-Lagrange equation will be the derivative with respect to time of the partial derivative of L with respect to x dot minus the partial of L with respect to x is going to be equal to 0. So we are going to be interested in calculating these components with the Lagrangian that we have here. Perfect. So let's calculate the first value. That is going to be, let's say, the partial of L with respect to x. What is that going to be? Well, looking that this element does not have any x, it's going to be 0. This phi depends on x, so we will get here minus q, the partial of phi with respect to x, and then we will get a plus qx dot, the partial of ax with respect to x, of course. So you should also remember that, this vector potential depends on x, y, z, and t. So that means that all the components of the vector potential depend on those coordinates too. Okay? Perfect. So that is why we are taking the derivative with respect to x of the vector potential at the component x. Okay? So then we should take the derivative, but now for these two other components. Look that ay also depends on x, so that means that we will have here plus q y dot, the partial of ay with respect to x, and plus z dot, the partial of az with respect to x. Okay, perfect. So with this, we can set that the partial of L with respect to x is going to be, what is it going to be? Well, we can see that this will be q times minus the partial of phi with respect to x plus the partial of x, the partial with respect to x, b dot a. Yeah, looking at here, we have the dot product between x dot, well, actually b and a, right? Because we have the x component of the velocity times the derivative of the x component of the a. Notice that here I'm taking the derivative of the product, but it is the same as b dot the derivative of a, because b is a constant, looking that it doesn't depend on x. So that's why we are taking the b inside the derivative. Okay, perfect. So this is going to be the partial of L with respect to x. Okay, perfect. So now we are going to calculate what is this element, the partial of L with respect to x dot. It shouldn't be so hard. With this Lagrangian, we will get that the first element is mx dot, and then phi doesn't depend on x dot, but this element does. So we will get plus qax. Okay, perfect. Yep. So then we should take the derivative with respect to time of the partial of L with respect to x dot. So if we take the derivative with respect to time here, of course, here we will get mx dot dot, then plus q, which is a constant, and then the derivative with respect to time of ax. So here is going to happen something interesting. Like we mentioned, we know that ax is a function of x, y, z, t. X, y, and z are functions of t. Okay, they change on time, so this will be something like this. So looking that these variables depend on time, well, we are going to use the chain rule to calculate the derivative with respect to time of ax. So this means that the derivative with respect to time of ax is going to be, first of all, the partial of ax with respect to x, and then the derivative of x with respect to time. But we know that is x dot. And then we will have something similar with the y coordinate. It is going to be the derivative of ax with respect to y, and then y dot plus the derivative of ax with respect to z dot plus, and then remember that we have here the derivative with respect to time of ax. Perfect. So we will get that the derivative with respect to time of the partial of L with respect to x dot is going to be mx dot dot plus q, and then times all this expression that we found here. Okay, perfect. So according to the Euler-Lagrange equation, we need to take all these, and then we need to subtract what we found for the derivative of L with respect to x, which is all this. Yep, and this is going to be equal to 0. Okay, so now we are going to work a little bit with this expression to see what are we going to get. Well, first of all, let's say that mx dot dot plus q, the derivative of ax with respect to x, x dot, plus the derivative of ax with respect to y, y dot, plus the derivative of ax with respect to z, z dot, plus the derivative of ax with respect to time, then plus q, the derivative of phi with respect to x, and we are going to write this dot product in the long form. Let's say it that way. We will have minus q, the derivative with respect to x of, it will be ax, x dot, and then minus q, the derivative of ay with respect to x, y dot, and then minus q, the derivative of az with respect to c, z dot. Okay, perfect. And here I should close the parenthesis, and then we can easily see that this element can cancel with this element. So I think that's the only element that can get cancelled. Recall that this is equal to 0. So what we are going to do here is to factor this q with the derivative of y and the derivative of ax with respect to time. So we are going to get that mx dot dot plus q times the derivative of y with respect to x plus the derivative of ax with respect to time, like this. And then let me factor again q here, and we are going to get, what will this be? It will be y dot that multiplies the derivative of ax with respect to y, and then minus the derivative of ay with respect to x, like this, for this element and this element. And then we will have plus z dot times the derivative of ax with respect to z, and then minus the derivative of a z with respect to, and here it should be an x, right? So with respect to x, and this is equal to 0. Okay, perfect. So with this we can easily get that mx dot dot is going to be minus q, the derivative of y with respect to x, plus the derivative of ax with respect to time, and then plus q times, let me write this here, plus q, the y dot here, the derivative of ay with respect to x, minus the derivative of ax with respect to y, plus z dot, the derivative of a z with respect to x, minus the derivative of ax with respect to z. Okay, and as you can see, here we have mx dot dot, which is known as the net or the total force on the particle, the mass times the acceleration. So this is giving us what is the equation of motion corresponding to that Lagrangian. And here comes the interesting thing. If you notice, for example, this expression, it can be easily see that it is the z component of the curl of A. Yeah, I mean, if you calculate this, you will get the derivative of ay with respect to x minus the derivative of ax with respect to y. So this is the curl of the vector potential, but it is the z component. And here it happens something similar, because we have here that this is the y component of the curl of the vector potential. Okay, so if you notice, we have here the y component of the velocity and the z component of the curl of the vector potential. It is the y and the z, and here we have the z component of the velocity, and then we have here the y component of the curl of the potential. So this is the y, this is the z. So as you can notice, this is something very similar to a cross product between the velocity and the curl of the vector potential. Okay, notice that, well, the curl used to have a minus here, right, to calculate a component of the cross product, but well, that is not a problem, because we can just take a minus here and then a plus sign here. So we can immediately identify this as the it will be the x component of the cross product between the velocity and the curl of the vector potential. So we will get the x component, looking that we have the y component times the z component minus the z component times the y component. Okay, so this means that, well, we can say that mx dot dot is going to be equal to minus q, and notice something here. We have the x component of the gradient of phi. So this can be seen as the gradient of phi x component, and then we will have here the derivative with respect to time of the x component of the vector potential. So it is the derivative with respect to time of the vector potential, but the x component, like this. And then we have here plus q times what we mentioned before. It is b cross the curl of a, but the x component. So what we have here is an equation that relates only the x component of some vectors that are very well identified in this equation. If we want to generalize this, well, we will get that here we are going to have for the three components f, yeah, because we have here the force, well, the x component of the force, right? But if we take the three components, then we will get the total force F. And then here we will have minus Q, and then the gradient of phi plus the derivative with respect to time of A, and then plus Q times B cross the curl of A. Okay, perfect. But if you remember, we defined that the electric field is equal to negative this quantity over here, which is exactly the same that we have here with this minus here. So this means that this can be seen as Q times the electric field. And then here we have what we defined as the magnetic field or the magnetic induction. So this can be seen, and here there is a parenthesis, right? So this can be seen as B cross B. Perfect. So we will have plus QB cross B, which is very well identified as the Lorentz force. Perfect. You know that this is a very famous formula for the force that is a particle feeling that is under the influence of an electromagnetic field, okay? It depends on the magnitude, well, the vector electric field, the magnetic induction, and the velocity of the particle, right? Yeah, this is one of the famous equations you see on first course in electromagnetism. So what this is telling us is that the Lagrangian corresponding to a particle moving on an electromagnetic field is given by this expression over here. Okay, we proposed a Lagrangian, then we took it into the Euler-Lagrange equations and got the Lorentz force, which is related to the force that a particle in an electromagnetic field is feeling. Okay, perfect. So that means that if we want to calculate the Hamiltonian of the particle that is moving in the electromagnetic field, well, we can just take that Lagrangian, and with the Hamiltonian definition, we can calculate that Hamiltonian. Recall that that definition is that H is equal to x dot, the derivative of L with respect to x dot, plus y dot, the derivative of L with respect to y dot, plus z dot, the derivative of L with respect to z dot, and then minus L, right? Because we know that, well, the general formula is that H is equal to Q dot, Qi dot, Pi and minus L, but you know that the conjugate momenta Pi is defined as the derivative of the Lagrangian with respect to Qi dot. So looking that we have a double index here, we know that this is talking about a sum, and that sum for our case is this one over here, because we are working with three generalized coordinates x, y, and z. So that means that this is the formula that we need to use to calculate the Hamiltonian. So let me bring back the Lagrangian definition to this page. Okay, perfect. So these are the two Lagrangians that we introduced at the beginning of the lesson. So we know that, well, we are going to have to calculate the derivative of the Lagrangian with respect to x dot, for example. we can easily see that this is mx dot and then plus qax. Yeah, right, and we know that this is going to be px. Perfect. So with this, we can say that x dot is going to be px minus qax divided by m, right? So this is going to be one of the first transformations we are going to need. And if for symmetry we calculate y dot and z dot as y dot equals py minus qay divided by m, and z dot is going to be pz minus qaz divided by m. Perfect. So here are all the transformations that we are going to need. Okay, so we are going to have that the Hamiltonian is going to be x dot times px, right? From this formula, recall that this is px. So we will have px that multiplies this thing over here, so that is going to be px squared divided by m minus qpx ax divided by m. Okay, and then plus, but well, we will have the same, but now for the y, right? So it will be py squared divided by m minus qpy ay divided by m, and then for the z we will have bz squared divided by m minus q bz az divided by m. And then due to our formula here, we need to subtract the the Lagrangian function, right? So let me copy all this. Okay, so now we are subtracting the Lagrangian here, but you need to notice that this is in terms of the dot variables, so we need to change that. And then we will rewrite this part of the Hamiltonian, and we will get that this is a minus 1 divided by 2m x dot squared, but that is px minus qax divided by m squared, and then minus 1 divided by 2m py minus qay divided by m squared minus 1 divided by 2m pz minus qaz divided by m squared, and then we will add plus q phi and then minus qx dot, but that is px minus qax divided by m, and then times ax, and then minus q, let's say ay here, and then py minus qay divided by m minus q az pz minus qaz divided by m. Okay, perfect. So we have a very big expression for the Hamiltonian, but you are going to see that a lot of terms are going to be simplified. The thing here is that, well, we need to develop these squares that we have. Okay, so let me rewrite this first expression again here. Okay, there it is. And then, well, like I said, we are going to develop those squares. So look that for here, we are going to get an m squared. So that will be cancelled with this m right here. So we will get an m in the denominator. So that means that here we will have minus 1 divided by 2m that multiplies px squared minus 2 px qax plus q squared ax squared. And then we will have the same for the y and the z element. So it would be minus 1 divided by 2m py squared minus 2 py qay plus q squared ay squared, and then minus 1 divided by 2m pz squared minus 2 pzqaz plus q squared az squared. Okay, and then for these three elements we will have that, well, we are going to make the multiplication to see what are we going to get. It will be minus q px ax divided by m plus q squared ax squared divided by m minus q py ay divided by m plus q squared ay squared divided by m minus q a z b z m here plus q squared a z squared divided by m. Okay, so I'm going to rewrite this expression on a different page. Okay, now I just rewrote what we had found for the Hamiltonian, and here is where we are going to start with all the cancellations. So let's first look looking that this element is divided by 2m. Well, we can cancel the 2's, and well, this can be cancelled with this element, because with this minus and this minus, with it becomes a plus, and then minus this, it is 0, right? So it will happen the same with this element and this element and this element and this other element here. Okay, perfect. That is the first cancellation. For now, there are no other cancellations, but we can simplify a lot of things. For example, let's look at this element and this element. We see easily that px squared divided by m minus 1 divided by 2m px squared is going to be 1 divided by 2m px squared, right? And again, that will happen the same with the y and z elements, so we will get here px squared plus py squared plus pz squared, right? So that is for this, and this. Okay, perfect. So look that again. Here we have a q squared ax squared and a q squared ax squared, and well, this is divided by m. This is multiplied by minus 1 divided by 2m, so we will get plus 1 divided by 2m, right, times q squared, and let me factor that q squared. Here it multiplies ax squared plus ay squared plus az squared, right? It is for this element, this one, this one, this one, and this, right? Okay, so what other thing we can do? Well, we will get a common factor minus q divided by m that multiplies px ax plus py ay plus pz az, right? Okay, so notice something. Oh, right, I forgot to add the element q5 here. It is very important. Yeah, but that doesn't imply any problem. So the thing here is that you need to notice that this whole thing can be seen as 1 divided by 2m times p minus qa all squared plus q phi. Okay, perfect. Because, well, if we square this, we will get 1 divided by 2m p squared, right? And then minus 2 times this, and then divided by 2m, we will get qp dot a divided by m, and then plus q squared a squared divided by 2m plus q phi. But recall that here what we have is the dot product between p and a, which is this element over here, and it multiplies q divided by m. And then this element is p squared divided by 2m, which is what we have here, and then q squared divided by 2m times a squared is this element here, right? So perfect. So with this, we have shown that this whole thing that we had can be rewritten as this, what we have here. And this is the final result because we already have the Hamiltonian of the particle under the influence of an electromagnetic field. Okay, perfect. Yeah, just recall that this P that we have here is identified easily as the linear momentum of the particle, While Q is obviously the charge of the particle, A is the vector potential, and phi is equal to, well, the scalar potential that is associated with the electric field. So again, this will be the expression of the Hamiltonian for a charged particle that is under the influence of an electromagnetic field. Perfect. So I hope you enjoyed this lesson, and I think this is a good moment to finish.